Hey everybody, it is November 2021 and you guys have submitted a lot of good questions in the month of October. So I thought I'll make another video, another lecture where I answer those top picked questions that I picked that I felt that are interesting and then answer them in detail. And I really enjoyed making the October video, and you guys seem to also enjoy it, and as it gives you this, it's almost like a live experience, almost, not quite. But how about we jump into your interesting questions? I'll try to answer as much as I can, but usually I always give it lengthy answers, right? Then all the questions that I'm going to go through are already answered, but I'll provide my own in-depth answer when I go through them. So one question 70 hours ago from Alex Wen. The question goes as follows: why can't I get bitmap index scan with the last equal statement? So this particular question is very related to one of the lectures. So they were trying to go through the lecture which I explained, bitmap index scan, and table scan. And they were following apparently they're following my lecture and they executing the query, but they were giving different results, and this is absolutely normal. Different result in terms of the plan. The database depends on the version, depends on the patch, depends on the nature of the query, depends on the statistics of the table at that point will give you different plan, but it better give you the same result, right? So when I do something, when I show you something and I show you that the database at that point chose that plan, in the new version of Postgres, it might decide to change their algorithm and pick a different plan. So just keep that in mind. With that out of the way, this is actually explainable. So here's the query they were executing, right? So here they're showing the grades table, which is around 1 million row here, and this is the query they were executing. Explain select name from grades where grade is greater than 95. Can we expand this? I guess we can. Maybe it's better this way. Yeah, where the grade is greater than 95, right? And the ID is less than 1,000. So just to go through the table again, the schema itself, and thank you so much, Alex, for giving us fantastic screenshots so we can go through this in a nice manner. So the grade schema is like this. We have an ID field, and this is the default primary key on this particular table, right? And it shows here grades primary key, right? So we have a primary key, that means it is unique by default, right, on the ID field. And there is another index on the grades for these students, and it effectively has just a normal index, and they are including the ID as part of the index here. So this is a non-key column, and this is the key column. All right, so the query goes as follows. It says, hey, where G is greater than 95, give me all the students that have their ID less than 1,000, and only of those 1,000, give me those who scored more than 95. All right. The query doesn't need to make a sense, right? But just understand what is it doing. And every time they execute this, they are getting an index scan, right? So the question is why they're getting an index scan. Well, they're selecting the name of those students. That's what they're doing. So the question is why, right? As opposed to a bitmap index scan. So what is a bitmap index scan? I already explained it, but it doesn't hurt, right, to explain it again. A bitmap index scan is a technique. I think it's especially in Postgres, but I think other databases implement them, where if there are multiple indexes, the database will scan the first index, but not to to get the actual rows from the index that satisfies a particular query. No, it finds the pages that might have those results, right? So because one page, and guys, you gotta watch the video that I just added in October. This is a very critical video where I explain what is the difference between a page, a table, a row IDs, all these things. These are fundamental building blocks that you need to understand. So when I mention them, they make sense. So a page have many rows, right? So the index will actually include two pieces of information when you find a particular value. It points to the row ID and it points to which page this row lives in, right? A bitmap index scan only takes note of the pages. So we'll scan the index, find all the candidate rows, but discard the rows and find the pages instead, right? So we're gonna come to why. The pages will definitely have more rows than the actual values that we pulled, right? They're gonna have more stuff and more stuff that we don't need, definitely. But here's the thing: it builds a bitmap kind of index, right? Of like a bit gate, where it says, okay, oh, and this gate is all zeroed out, and if it detects like, oh, as a result of this scan, I found page 0. I need to pull page 0, page 1, page 17, page 19. That's what it does. Does nothing else, right? And then it scans the other index. Says, okay, I'm gonna now scan grade 95, right? Whatever. That's a different index. It does exactly the same thing. It says it takes note of what pages it needs to pull. So it's gonna pull. Let's say we said 0, 1, 2, and 17 for the first index. The second one is I don't know, 3, 4, 5, and 17. Let's say, for example. So the second index gave results 3, 4, 5 pages and page 17, and the first index gave 1, 2, 3 and page 17. Now the Postgres says, okay, we need to AND. AND is the best thing you can do in a query. AND eliminates a lot of garbage. And in this particular thing, we AND those results. When you AND, means the row must exist in both index search space, right? So if you have a row that exists in, you found it as a result of page 3, but not in the first index, then you just eliminate it. As a result, the only page that's shared between those two indexes is page 17. So the Postgres will discard page 0, 1, 2, and will discard page 3, 4, 5. Discard means eliminated from the result, and just literally takes these two bitmaps and does an actual AND between them. So 1, 1, 1 is gonna be ANDed with 0, 0, 0, and you're gonna end up with a new bitmap with only bit 17, which correspond to the page 17, to be pulled. So you go and fetch just that page. Beautiful. So now when you go back, this is called a bitmap index scan. No, this is not enough. You go to the heap. Now you have to go to the heap, and I talked about what a heap is. Go watch that video. And now when I jump into that heap and pull page 17, I have to reapply those filters, and this is called, usually when you see here, it's called filtering, right? You apply a filter on the heap itself. So you pull page 15, and then now you pull all the rows in page 17, and then manually goes through these rows and then filter out, okay, I need ID 1000 and whatever, I need ID less than 1000 and grade more than 95. And since you have the G and the ID in the heap, you have everything. You can definitely do this filtering. That's what a bitmap index scan. So sometimes Postgres will decide to do that, right? To optimize certain situation. And this seems like a case where it should, right? There is an AND. There are two indexes to scan. Why did Postgres didn't use the bitmap index scan? So what Postgres thought here says, you know what? We could be smarter than that. Because bitmap index scan can be expensive because you're scanning two indexes, right? Look what Postgres did here. Postgres looked at this and says, oh, wait a second. you're querying, you want IDs less than 1,000. And Postgres actually have statistics. What is the ID? ID is a primary key. When you say ID is a primary key, that definitely means it will have some statistics that says, okay, is this a positive integer? It will. That means the values must be that we're going to look at between 0 and 9999. We will only need 999 rows at maximum. So the moment Postgres realizes that it's going to only work with 999 rows, it automatically flips. Says, wait a second, I don't need to do a bitmap index scan. Let me go. I don't even need to scan use the other index. I don't care. Let's scan the ID, the primary key, pull all the ID less than 1,000. So now you're gonna have a lot of rows, right? Rows from 0 to 999, but not all of them is the actual results that you want. Some of them will have grades greater than 95, some of them will have less, right? So you need to be careful of that. So what Postgres does is, okay, now I'm gonna pull all the pages, right? What pages do you need to fetch, right? Because I need to go to the heap anyway, right? To do this result, right? Because they need the name. The name is not in the primary key ID field index. So now it takes mark of what pages need to pull and goes to the heap and pull those pages. And it should be a page or two, or maybe less. It depends on them, on the size of the rows and all that stuff. And then pull these pages. Now, what it does, it just goes through them and then literally just applies this query. Okay, since we fetch the heap, we have the grade fields. Let's just filter them manually. And this was way faster, Postgres decided, than actually using bitmap index. Because the result is so small. If Alex increased this to more than 1,000, I don't know what the number is, to be honest, because it's an implementation detail. Who knows? It's heuristics at the end of the day. If it means ID less than 10,000, 20,000, 30,000, then Postgres, 30,000 is a lot of rows. I'm not gonna scan an index and then go and fetch all the rows. Maybe I can eliminate some pages by doing a bitmap index. All right, guys. So that's one question that I found interesting.
Apologies for the change of scenery and the audio quality. I'm currently traveling and my video was cut due to something. I had to take care of something, but I had to finish the lecture for you guys. The Q&A for November 2021, and we have a very interesting question here from Rakesh, and it's a three-part question. So we're gonna try to answer this question, and then just call it a day. How about that? Because it's just there is no time to go through more questions. And guys, let me know, how do you enjoy these kind of content? I think it's beneficial. So the question goes as follows: how to choose the order of columns to create a composite index? So hi Hussein, my question has three parts. If I have a query that does a filter on say 10 columns joined by an AND, is it advisable to have a composite index on all 10 columns? Let's assume for simplicity that this is the only query for this table. So think about this, right? I already answered this an hour ago, but it's always good to kind of add more details when we explain things like that. So when you create an index, specifically composite index is just an index on multiple columns. And the way it is designed, it will be these columns, all the values of these columns will be added together as a tuple, right, in the index, and indexed accordingly. So it means it really depends on the data type of what are you indexing and the number of columns you're indexing as well. And this increases the index size, because if you're indexing a lot of columns, that means all these entries, if this is a string, this is an integer, float, all adds up really to the size of the index. And I might say, Hussein, what does it matter? The index size. I have all the space I need, right? I have, I don't know, 1 petabyte of disk drive, and I don't really care. Well, we're not talking about really storage. Storage is not an issue anymore. The issue is the I/O, right? Because your I/O will be slow, whether it's an SSD. Well, SSD it's much better than a hard drive, but you want to minimize those precious I/Os because if an index is large, and when I'm talking large, I mean really large. If you have 500 million rows and you are indexing 10 columns, then the index will be proportionally large to the size. Not going to be as large as the actual heap table, but it's going to be large. Large index means that data structure won't be able to fit in memory. Now, large indexes won't fit in memory. And if they don't fit in memory, they have to be put in disk. And when they are put in disk, to read and scan the index, you need to go to disk, right? And you need to read page by page or whatever how number the file system allows you to. And that gives you a finite amount number of index entries to read, right? So the larger the index columns, right, the more pages you need to read, and that slows down. So that's the first thing, right? It's just the additional IOs you want to do because of the increased size. Another side effect of having many columns, again, I'm just saying what is the side effect of what you're proposing, Rakesh, right? Having an index on many columns. The side effect is the write amplification that happens as you update your heap table. When you update your heap table, right, you insert a new entry, this index is touching a lot of columns. So any update to an existing row that touches this column will have to update the index. Any new row you insert will have to update the column. Well, it depends if these columns are nulls or not. The index might not need to be updated, or if you have like a partial index uh, where you're only indexing certain where clauses, that also might not need to update the index. But regardless, you need to update the index in these particular situations, right? So that also adds, not necessarily to a performance point of view when you're updating the index, right? It's not slow to update an index, right? It's just an extra IO to the right that is almost negligible. Yeah, it adds up a little bit, but in a batch mode, that slows things down. But it's really negligible when it comes to one-off edits, right? The side effect really becomes when you when you when you try to bulk update this, right? You're touching the index, and that results in a lot of writes, and that writes, especially in a replication uh, environment, if you're trying to push all these writes, then the bandwidth, increases, and bandwidth increases means more network latency. And then when you think about that, that's what Uber complained about with Postgres compared to MySQL. Postgres had way more write amplification compared to uh, MySQL, for example. So they went one route, to minimize the write amplification because network is precious. And guys, this is what I want you to think about. Anything you do has an effect, and you don't need anybody to tell you any of this if you understand the fundamentals. And when you actually get this course, you understand the fundamentals. You don't need me, right? It's just because, like, hey, say I can answer any question because, hey, I understand the basics. And once you understand the bare metal things, you can just answer any question. Just like, oh, because of this, this will result. This will be the result, right? It's just cause and effect. So the second question is the query planner smart enough to arrange the filter in order that will be subset of the composite index? Yeah. So for example, if I have a composite index on ABC, right, we talked about that. Right? If I have A, B, C, D, the order does matter. I talked about that in another video. The composite index has to be from left to right. and they will be built from left to right. So if you're searching on uh, so Rakesh is asking, is like, what if my word clause started with C equal 10 and A equal 20 and B equal 30? It doesn't matter. And is interchangeable. So planners better be smart enough to understand that C equal 10 and A equal 20 is the same as A equal 20 and C equal 10. Well, that when that includes ors and ands and all, that obviously based on discrete mathematic formulae, that changes, right? Right, but just discrete algebra stuff. But when it's L and, doesn't matter. You can interchangeable. So don't worry about it. As long as you actually search for A, right? If your stuff is only C and B, right, and A is not included, this won't hit the index, right? And you probably know this. Is there a best of practice for the order in which the column or order for composite index be chosen? Uh, this really, there's no best practice really when it comes to these kind of things. Like really, uh, if you're querying from the leftmost columns, if you're querying a certain field, and that field is the lonely field that's being queried, I suggest putting that to the left because just it's all logic at the end of the day, right? Uh, what is the minimum subset of filters that you're querying against? Put that at the as the left side column, right? So that means you need to understand the nature of your queries, right? At the end of the day, the nature of your queries are very very critical to kind of. That's why backend engineers have to work with the front end engineers to know what kind of. I guess the front end engineering don't normally issue backend SQL queries, but just understand how the filters, how the where clause are being executed. That's why I really don't like to use ORMs because they execute just abstractly leaking the back end and execute queries that we have no idea. It has a mind of its own, right? It hides the complexity and as a result adds more and more performance penalty that we engineers love to see, right? I just need to see everything. I you probably know this from my YouTube channel. I really don't use ORMs. I don't like to advise anyone against anything, but if you want to use an ORM, right, use it, but understand how it works. Completely understand how it works. You have to understand complete anything component that you use. You really understand what is it doing. If you're using it blindly just to uh, save you a couple lines of code, that's in my opinion, that's a bad practice. Never use a code to uh, libraries just so you don't want to write an extra couple line of codes, right? If you understand that this actually saves you this and you know how it works without it and you can build it without it, then yes, absolutely, I'm fine with it, using an ARM or any framework for that matter. It just my problem becomes when you don't understand what this thing is doing. It hides a lot of complexity, but as a result, things leak. These complexity leaks to the front end all the time. Leaky abstraction. Google that. You'll find my video on that topic. Um, yeah. So, is it a good idea to create a single column with a 10 column index? It really depends, right? How big are the columns? Really, how complex are the data types? But you can try it and see if it's affect you. But normally, 10 columns is a lot, right? So if you really understand the queries, my guess is you won't need 10 column indexes. Just because something is in the where clause doesn't mean it has to be indexed, right? Because when you do an and, especially the database, think about this. Like, let's say if you're doing C equal 10, just saying C equal 10, you just eliminated anything that is not C equal 10, right? But now, then, because you're using an and, this also eliminates a lot of other rows. So now you're working with a subset of the table, kind of, right? So now if you add to that another filter, A equal 20, then you just eliminated maybe another bunch of rows, right? Think about this. how much rows are being eliminated. If by here you eliminated, I don't know, by here if you are left with 10,000 rows, I would say, yeah, maybe just add another index, right? Because now this will eliminate it to 3 rows, right? But if you added these two in the index and you are left with, I don't know, 2 rows, this is absolutely useless because what, 2 rows is going to be eliminated in 1 row? Yeah, I rather just jump to the heap and fetch the page and then filter the extra one. Even if it's 1,000, even if it's a fifth, I mean 2,000, that's okay, right? So understand the statistics of that table. And I think I'll leave it at that, guys. Thank you so much for watching. Enjoy the course. Goodbye.